Hello and welcome to this video, and in this video we're going to look at the final parts of simple harmonic motion. We're going to look at resonance and damping. So far what we've looked at is examples of simple harmonic motion just as a general idea. We defined what it is. We looked at displacement time, velocity time and acceleration time graphs. We then looked at how the energy changes as a simple harmonic oscillator oscillates. Then we looked at specific examples of calculating the time period of a pendulum and a mass spring system. Now we're going to see something that we've done for all of these things, and then we're going to say what happens if we don't do that. And the thing that we've done is we've let them all oscillate freely. We've just pulled it to a starting position, we've let go, and it's just swung back and forwards as freely as it wants to. So this is what we're calling free oscillations. Okay, and free oscillations are where it oscillates with no forces applied, so no external forces applied. So we haven't pushed the pendulum at any point, we haven't pushed on the mass spring system or pulled the mass spring system down except to start it in both cases. So we've just left it to do what it wants to do. But what happens if we do apply some force? What happens if we push it at a certain point, and how would that affect not only the time period of it, but it would affect the amplitude of the oscillations, and how would it affect everything? So now we're going to look at what happens when we have forced oscillations. And forced oscillations are where we're going to apply a periodic force with some frequency. Now what I mean by this is, if it is periodic, the same way that the motion of the pendulum and the mass spring system is periodic because it will continue to have the same time period, we're going to apply a certain force at a certain time with a certain frequency. So we might do it once per second at the same time. Now there are two ways that we could apply this force. When we think about a periodic application of this force, we're thinking about sine waves. Now we looked back in waves that we could have two waves that are either in phase or out of phase or in antiphase. Now if we apply that phase kind of idea to this case, if we apply a force to a pendulum while the force is in phase with that thing, okay, we can take a case, an image of that, and look at what would happen. So let's take a more of a realistic example of when we're actually going to push a pendulum. Let's just say we have a swing, okay, and there is someone on this swing, and this is you over here, and there's a person on this swing, and they come up to the top. They're going to follow this kind of path where this is their equilibrium position. That's probably a bit of an extended path. They're probably going to follow something more like this. And now if you want to apply a periodic force, so applying forces in phase with the oscillations, if you apply a force in phase, what does that mean? Well, it means that you're applying it at the same frequency that this thing would naturally oscillate. If you were to just let this swing go and stop pushing, it would naturally oscillate back and forth with some frequency. Now we obviously know in the real world that it would slow down and it would eventually come to a stop because of friction, but in the cases that we're talking about, this is simple harmonic motion. We don't have friction, so we're saying that this would actually go on forever. If you just let this person start and they didn't kick their feet or anything, it just let it swing, they would continue to oscillate back and forward forever. Now what we're saying is we're actually going to push them. Now we obviously know if we were going to push them, we would push them every time they reach the highest point on our side, and that's every time it ends a time period. So that means what we're doing is we're applying a force. So in this case, the force applied is or has a frequency which is equal to the natural frequency of this oscillations, which is equal to the natural frequency. So what I mean by natural frequency is if this was a free oscillation and we just left it, didn't apply a force, then we want to apply a force that is in phase exactly at the time where it reaches the maximum point. And what happens when you push someone on a swing each time? They go higher, right? Your amplitude of this oscillation is going to increase. So this leads to an increase in the amplitude. And this whole idea is resonance. Resonance is where we have some sort of periodic motion and we're going to apply a force to it in phase with those oscillations so that we can increase the period or increase the amplitude of those oscillations. Now, in terms of how we can identify resonance, or what we could more formally narrow all this down into, is resonance is applying a periodic force in phase with the natural oscillations of an oscillator. Okay, so in order to, if I scroll down a little bit, we're going to say that we could actually match up how the amplitude will change as we change the frequency of the force that we're going to add. Okay, so we're going to say this axis here is the amplitude and this axis here is the frequency of the forces that we're applying. Now we'll find that if we apply a force that's less frequent, and actually we'll end up with some of these frequencies will be out of phase. So if we apply a force that's less frequent but still in phase, we'll end up with a slightly higher amplitude. That means that we're just saying maybe every 10 swings we'll push once rather than every one swing. But if we were to do this and we were to apply it in antiphase, instead of letting it come to the top, we might stand in the middle, and then every time they come back like this, you're just going to push them this way again. So you're not actually applying a force to push them, to accelerate them, you're actually decelerating them by applying a force in the opposite direction to where they're actually traveling. So if we apply them in phase, we're going to end up with some graph that's going to look roughly like this. Okay, if we do it too quickly, we're going to end up decreasing the amplitude because before they've had time to reach the height that they're supposed to reach, the maximum height, we've pushed them back the opposite direction. And if we do it too slowly, then they're just going to, we'll be putting it so they can't actually reach the maximum because we're not putting in enough force for them to reach that maximum. But if we apply a force exactly equal to the natural frequency, which I'm going to call F0. So F0 is the natural frequency of oscillation. Then we see that we get the maximum possible amplitude that we could possibly get out of that. And that is, F0 is therefore referred to as the resonant frequency. Okay, so if we apply a force in phase to a natural frequency such that it means we have the maximum amplitude for those oscillations, that is referred to as resonance. Okay, now on the flip side, we can investigate this idea a little bit more of what happens if we were to actually stand in the middle and apply forces out of phase. So let's draw out this swing. So we have this is your 0 point, you have some child on a swing here, and then you've got someone pushing them. We've just said that if we were to push them at this position in phase, they would end up with a larger amplitude. Therefore, if we apply a periodic force, out of phase with these oscillations, we're going to end up with a smaller amplitude. Okay, this leads to a smaller amplitude. Okay, and the way we're going to say this is out of phase, like we said just now, if we were to instead have this child every time it reaches the middle point here, we're going to then push it back up here. It's only going to oscillate back and forth. It's never actually going to reach a maximum because it doesn't have time to gain all of that energy back into another form. It will just keep being pushed in the same direction. And so not only are you going to get a damping force, you're also going to get not simple harmonic motion because it's not oscillating anymore. So if we apply a periodic force out of phase, we end up with a smaller amplitude, and that is what we call damping. Okay, this is damping. Now, damping is, in the case of a swing, not very useful. Okay, in most cases where you have like fairground rides, damping probably isn't the thing you want because you're trying to get that adrenaline rush. You don't really want things to be stationary. But damping in other cases is very useful, and that's why we have 3 different forms of damping. So we're going to refer to this. Now these expressions for the damping will change. I'm going to refer to them as heavy damping, light damping, and critical damping. Okay, now you might hear this said as overdamped, underdamped, and critical will probably say the same. Okay, so damping as an idea is just where we're applying a periodic force out of phase in order to reduce the amplitude of oscillations. Now, if we were to look at how the amplitude is going to change over time with heavy damping or overdamping, this is the amplitude, this is the time. The way heavy damping works, or the way you can visualize it, is imagine you're bouncing a basketball and then you just want to stop the basketball. So currently it's oscillating up and down, almost like a mass spring system, but you're just going to completely push it. So keeping, like, let it bounce, but completely just lower your hand down. And so the basketball is going to start by oscillating up and down. Then as you push it down, it will oscillate down, but with a higher frequency. And eventually it's just going to continue to bounce up and down before it eventually stops on the ground. Okay, so the amplitude of this, or actually let me just write this as the displacement of this. We start like this, but we're actually going to crush the amplitude of this pretty quickly, but it's still going to oscillate, right? So it's still going to have something that looks like this, but it will come back to equilibrium. And that's the whole point of these damping things. We want it to just remain stationary. Okay, so this is an idea of what overdamping is, or what heavy damping is. We're trying to get it to stop straight away, but it will continue to oscillate for a little bit. Now, light damping is pretty similar, except light damping is going to take a lot longer. Okay, so in this case, we've had this over quite a short time span. Light damping would be something more like if you were to just start applying less force to the ball, and so you'd eventually end up with smaller and smaller oscillations because you're not letting it bounce high enough, and then eventually it will start to just dribble along the floor. So you're going to end up with something that's just going to take a longer time, so you'll end up with something that's going to do more like this. Okay, so notice the amplitude is decreasing, but it's just going to take a lot longer, and actually it will go on until it will eventually, so let me put here, will reach 0 eventually. Okay, now heavy damping and light damping aren't exactly the most useful things for everyday use. We don't really want things to oscillate too much. Usually damping is used in the case of a mass spring system in things like suspension. If you're in a car and you go over a speed bump and your suspension works by heavy damping, you're going to continue to bounce up and down for a bit until then you just start vibrating, and then you're going to come to a stop. Obviously that's not going to be comfortable. If you do it by light damping, you're going to end up just bouncing up and down along the road for, I don't know, another few hundred meters, which again, you don't want to be bouncing up and down in a car. You want the ride to be smooth. And so these two damping effects are not always the most useful. Critical is usually the one that people will go for, and that's because critical reduces the amplitude as quick as possible. Okay, so there is no oscillations with this. As soon as the displacement comes up, the critical damping takes it straight back down, and it goes straight back to the equilibrium position and stops oscillating. So critical damping is usually the most useful. Okay, that's not to say that there are no uses for heavy damping and light damping, but it does mean that critical damping is probably the one that they will use the most in exam questions. So it's probably the one you want to get your head around the most. So critical damping, if we continue with this basketball analogy, is you grab the basketball and you just put it on the floor, right? You don't bounce it towards the floor. You don't hold it as it goes down. You literally just grab the basketball and you place it on the floor. And that would be critical damping. Now, the last thing I want to do is just put these side by side and apply a few uses of these so we can get an idea of how they're going to be applied in exam questions. So let's say we have uses of resonance on this side. Resonance. And on the other side, we can have the uses of damping. Now, we've already said 2 examples. So one use of resonance could be a swing. We ideally want a swing to be pushed at its resonant frequency so we can get a high enough amplitude. And we said damping we can use for suspension in a car. Some other uses of resonance. We could have basically any type of musical instrument does resonance. And actually, this isn't quite a simple harmonic motion effect. This is now expanding resonance to be more of just an overall effect where we have things that are in phase with each other that will build the amplitude. So, for example, in a guitar, an acoustic guitar, you'll have the body of the guitar will continue to basically fly around all of these sound waves inside that have the same frequency because they come from the same sound wave. Therefore, they will build up, they will constructively interfere, they will end up with a larger amplitude. We could also have things like, if you've ever seen any kind of comedy really where they sing and the glass shatters, the way that works is by resonance, because the voice, the person who is singing is hitting the natural frequency of the glass. If you ever ping the side of a glass, it makes that nice frequency sound. If they then match that frequency with a sound wave, the sound wave oscillates the particles in the glass at their resonant frequency, so the amplitude comes high enough for the glass to actually shatter. You could also have speakers. Speakers work by resonance. You have large vibrations, large oscillations of the amplifier, so the actual unit of the speaker that vibrates up and down to cause these variations in the air pressure, which are the sound waves. They use resonance. So that could be another example of resonance. Examples of damping you will probably find to be much less common in their uses. The biggest one is obviously going to be suspension. Suspension is the one that they will most of the time go to. However, damping is also used in cars for the speedometer. So speedometer also uses critical damping, so that when you have that initial acceleration, the speedometer goes straight up to its point and comes back down to 0. It doesn't oscillate between the 2 points, because obviously that wouldn't make any sense. The final example that I think you would encounter in like an everyday use is door stops. If you've ever maybe your doors at school, maybe even your doors in your house, you'll probably find that some doors will close very smoothly. Some of them will swing back and forth when you close them if it's a two-way door. Some doors don't have any at all. But you can use a door stop to slowly bring the door to a close, and that would use heavy damping, because you're going to basically slow down the oscillation so it goes slowly, rather than where critical damping is where you try and get it as fast as possible. So door stops. But a lot of these you won't actually ever come across in your physics career. You'll just find that they'll come up with some sort of situation where it will resemble some sort of resonance or some sort of damping, and they'll ask you to be able to basically tell that it is resonating or that it is being damped, and then you can do all your calculations from there. Thank you for watching.